Steve Smith, Director of NOAA's VLab, here for the June edition of the VLab Forum, and we're coming to you live from the beautiful, the VLab Forum studios here in beautiful downtown Silver Spring, Maryland, in the shadow of the giant acorn. I'm joined here in the studios by John Chattel, our logistics manager, production manager. To remind everyone, the VLab Forum is provided as a area for discussion of topics for R2O, research to operations, and vice versa, relevant to National Weather Service operations. So we provide this as a area for providing situational awareness on things that are somewhere in the pipeline, moving their way to higher levels of readiness towards transition to operations. Some things are in their nascent stage, others are well along and very mature. So our format, to remind everyone, is about 30 minutes of content and then followed up by a question and answer session. During the content part, we ask you sort of hold your questions unless it's a specific clarification question. During the Q&A, we will provide the opportunity to use the raise your hand feature of the GoToWebinar. If you use that, then we will unmute you and you can ask your question directly to the speaker. You can also use the chat feature to provide a question, in which case we will provide your question on your behalf by reading it to the speaker. As a further reminder, this session is recorded and will be uploaded to the VLab Forum website shortly after the conclusion of the session. So without further ado, today's speaker is Keith Sherburn from North Carolina State University, also affiliated with the National Weather Service Forecast Office in Raleigh, North Carolina. The topic he's going to be speaking to today is improving understanding prediction of high-impact weather associated with low-topped severe convection in the southeastern United States. There's a bunch of people associated with this project, and I'm sure Keith will allude to them. Without further ado, though, let's just hand over the presentation to Keith. Keith, you there?
Sure am. Yep. Thank you, Steve.
Okay, go right ahead.
All right. Well, thanks to the VLab Forum for having me, and for Steve and John for setting things up today. And also thanks to all of you for tuning in. Today I'm going to give a brief overview of an ongoing C-STAR project that is focused on low-top severe convection in the southeast U.S. This is the second C-STAR project that's included a focus on low-top severe convection, which is also known as high shear, low cape severe convection, which I'll be calling it that throughout much of the talk today. This is a collaborative effort between NC State University, where the PIs and students are all from, and then also several national and regional collaborators across the eastern region and southern region of the National Weather Service. So digging right into the problem of high shear, low cape convection, first of all, the big issue is that it is a significant forecasting challenge, both nationally and locally. These environments account for a large fraction of EF1 or greater tornadoes and damaging straight line winds during the cool season. As you can see here in the diagram to the left, these darker reds here indicate a higher fraction of the total EF1 or greater tornado and significant wind reports that occurred within high shear, low cape environments. And you can also see that they especially occur during the overnight hours. And this is particularly an issue over broadly the southeastern U.S., roughly from the deep south up through the Ohio Valley and eastward into the mid-Atlantic, where the bullseye of this such activity lies. And the unconventional timing and marginal environments associated with these reports do contribute to a relatively low probability of detection of tornadoes, and also a fairly high false alarm rate of tornado warnings, as shown in some recent work by Anderson Fry et al. So just note in general that as CAPE decreases here in these plots on the x-axis, you tend to get into that lower POD and higher FAR portion of the parameter space. So how are we addressing this issue with this C-STAR project? Well, it boils down to 5 different components. And First, we wanted to identify any defining characteristics of severe and non-severe high shear low CAPE events and how they differ, followed by an assessment and improvements of the recently developed severe hazards in environments with reduced buoyancy parameter, or the SHRB parameter, which was just basically a combination of low-level lapse rates, mid-level lapse rates, and also shear vector magnitude, either 0 to 3 kilometer or effective shear. Then after that, we wanted to perform some case simulations using the WRF model to both study the mesoscale and synoptic scale evolution of these cases and to determine the resolution required to adequately simulate this convection. And there are additional ongoing simulations that are meant to investigate the storm scale dynamics of high shear low CAPE convection, which is in this process studies 2. We also wanted to determine the sensitivity of the convection to the base state environment. And finally, work using dynamical statistical downscaling to investigate the predictability of high shear low CAPE hazards such as tornadoes is also ongoing. So beginning with the composites, I want to just focus on the key points here, which are summarized with the conceptual diagrams on the right. First, I should note that these were created using the North American Regional Reanalysis dataset. And we used the data that was associated with EF1 or greater tornadoes and significant wind reports. So those were our severe report cases, in addition to false alarm warnings, which were our non-severe events. And we found that overall, stronger and more closely co-located features were found in the severe report data set. So that's particularly in terms of synoptic and mesoscale forcings for ascent, such as the near surface cyclone, upper level jets, upstream vorticity maxima, and so forth. And this was a critical discriminator between the severe and the non-severe events. And the importance of these forcing mechanisms, in addition to some of the process study simulations that I'll be exploring shortly, suggests that either the release of potential instability or strong low-level theta E advection played a large role in what we found was pretty rapid environmental evolution ahead of this convection. But it's also important to note that low-level lapse rates and shear vector magnitudes, which again were key components of the SHRB parameter that was developed a few years ago for these environments, continued to show discriminatory skill. And the MOSH, or the modified SHRB, which is shaded here in the conceptual diagrams, this parameter combines these established parameters of lapse rates and shear with a proxy for the release of potential instability, or just more generally forcing. And overall, it shows great discrimination between severe and non-severe events and cuts down a little bit on the false alarm area that was a considerable issue with the SHRB parameter. So as noted, the MOSH combines these low-level lapse rates here and shear vector magnitudes. In this case, this is the 0 to 1.5 kilometer shear vector magnitude, with a proxy for the release of potential instability to create this new forecasting parameter. And this proxy combines the theta E lapse rate over various layers with the omega at the top of that layer, and that goes from 0 to 2 kilometers up through 0 to 6 kilometers. We take the maximum value of that product and include it in the MOSH. And note also that the MOSH-E here on the bottom also includes the effective shear magnitude. So we've seen this recurring theme of low-level lapse rates and shear vector magnitudes being skillful in discriminating between our severe and non-severe events. But we don't have a really deep understanding of the processes that govern these sensitivities just yet. So that's kind of looking forward motivation for the second set of process studies that I'll discuss later that focus more on the convective scale dynamics associated with these cases. Now, it's worth noting that the MOSH-E is now available on the SPC mesoanalysis in beta form, as is the original SHRB parameter. The values for the MOSH-E do seem to be running a little hot, which may be related to the low bias of the values of effective shear that we calculated with the NAR data set. So it's possible that adjustments may be necessary in the future to sort of tune the parameter for use with the SPC mesoanalysis, such as with this effective shear term, or by maybe capping the contributions from the low-level lapse rate or the potential instability terms in an attempt to remove some of the false alarm area and get those values closer to the distributions we were seeing within the NAR data set. And capping the values, that's something similar to what is done currently in significant tornado parameter and supercell composite parameter for some of the terms, just to basically limit the contributions from those specific terms. So for now, the MOSHI is worth monitoring for high shear low CAPE events, but ultimately it's probably best to focus on the location of the maxima rather than the exact values right now, since they do seem a little bit higher than the distributions from the NAR data set. So moving on to the process studies now, the first set of process studies. These were conducted using the WRF model, and we nested a 9-kilometer domain and a 3-kilometer domain. The requirements for the case selection for these particular cases were at least a slight risk for severe convection from the SPC, along with mesoanalyzed CAPE no more than about 1,000 joules per kilogram, and 0 to 3 kilometer shear of at least 18 meters per second. So these criteria were a bit different than prior cases, but they still fall within the broader high shear low CAPE spectrum that has been discussed a lot over the last 10 to 15 years or so. Overall, there were 6 non-severe events which had no storm reports, and 11 severe events which ended up having multiple severe reports given these criteria. And as noted, these simulations were performed with the WRF, the ARW WRF, with 50 vertical levels, and the NAM analyses were used as initial and boundary conditions. And the simulations here were performed for at least 30 hours so we could ensure that you had relatively organic evolution of the synoptic and mesoscale features. So getting into some of the results, these animations show the surface theta E in the shaded field, along with 10-meter wind barbs, and the 40 dBz contour is shown here in the purple. On the left, we have a severe event, while a non-severe event is on the right. And these cases were both associated with a cold front, so there was continuous linear forcing associated with both these cases. And I'd say the biggest feature of note, or the most noteworthy feature here, is the rather narrow zone of enhanced theta E and also theta E advection immediately ahead of the cold fronts and the convection in the severe case. Comparatively, the feature is there in the non-severe case, but it's generally more diffuse. Also, the theta E advection here covers a broader area ahead of the cold front and severe event. You can see eastward into Indiana and Ohio, you get this continued increase of surface theta E as the line of convection approaches. You don't really have that as much in the non-severe case, much weaker advection overall, well ahead of the front. So overall, that is one of the key features that we found, was this really rapid increase in surface theta E immediately ahead of the severe events. Now, on the other hand, here's a case with more isolated convection, so you didn't have that linear forcing mechanism throughout the entire case. And a few features are apparent here. First, the higher theta E warm sector here in the severe case is a little bit broader and more expansive when it's compared to the non-severe event. Additionally, you have ambient flow overall that's a bit stronger in the severe event, with the 10-meter winds near or exceeding about 20 knots routinely. So that could help out, one, with advection, or two, just with the production of severe winds in this case. And also, it's worth noting that the cold pools in this severe case tended to be stronger. We haven't looked a whole lot into that feature yet, but that's certainly something worth noting and could lead to, or could at least help out with the production of some low-level mesovortices in some of these cases. So we know that this increased surface theta E that we were seeing in the severe cases particularly could lead to an increase in CAPE, and that could be a result of either increased temperature or increased moisture, or it could be both. However, you could also get an increase in CAPE as a result of decreased temperatures aloft or the release of potential instability. So determining which processes that are most important in these CAPE increases ahead of convection is pretty critical given that the severe events tended to have a much more substantial increase in CAPE, as you can see here in the box and whisker diagrams, in the 3 hours leading up to the arrival convection. And if you look at just the time series for the severe events versus non-severe events, you can see quite a bit of that destabilization actually occurs in the hour or so leading up to the convection's arrival. So we're getting at a point here where if you're looking at 3-hour model output, for example, you may miss this destabilization entirely. Also, the spatial scales at which this destabilization is occurring, whether it is due to that theta E advection or the release of potential instability, which I'll talk more about here shortly, spatial scales of those are going to be close to unresolvable or at least poorly resolved in a lot of your modeling systems. So ultimately, this may be one of the challenges with high shear CAPE environments is you might be getting destabilization more rapidly than you could actually observe. And it's certainly interesting because there have been cases that I've looked at, observed cases, where you have a sounding roughly an hour before you get severe convection, and there is no CAPE in that sounding. And same sort of thing when you look at SBC mesoanalysis data. You can have cases where you have 0 CAPE, and then an hour or so later you get a tornado or a significant tornado even. So this is certainly something to keep an eye on, and certainly a reason that we're seeking more observations in these types of cases. So when breaking down the CAPE increases by their potential source, we found that every event and every non-severe event saw an increase in surface mixing ratio in the 3 hours leading up to convection, and that's in the green bars here. But the difference here is in the surface theta field. So each severe event saw at least a modest increase in CAPE due to warming near the surface, while every non-severe event, or nearly every non-severe event, was essentially unchanged or even cooled in the hours leading up to convection. So this suggests there may be, despite the overall increases in CAPE for some of the non-severe events, there may actually be a stabilizing trend in the low levels. Now, in terms of upper level cooling, a handful of cases actually saw this as one of the primary contributors, or even the largest. Severe event 9 here and severe event 1 is actually the largest contributor. So this does indeed mean that the release of potential instability, which we found in the composites was important, could play a significant role in destabilization in the last few hours leading up to convection within some of these cases. And here's just one example of how the soundings evolved leading up to the arrival of convection. This was basically the night of January 29th into the morning of January 30th, 2013. There was a big tornado outbreak in Middle Tennessee that occurred within a high shear CAPE environment. And this was one of those situations where 3 hours before you didn't have much CAPE at all, especially in the low levels. But overall, you do see that increase in surface theta and that increase in surface mixing ratio in the few hours leading up to convection. But you also get cooling and moistening aloft, presumably due, at least somewhat, to the lifting of a potentially unstable sounding. You had very moist low levels. Atop that was a fairly dry layer. So if you get some layer lifting or just synoptic scale ascent in general arriving, you could lift that layer and produce some instability. And this can also be examined using time series line graphs, which show that as you approach the time of convection in these 4 cases, you do indeed see an increase in vertical velocity. You see a moistening and a cooling trend aloft, and you see a stabilization, of the theta E lapse rate. So these features all taken together are also indicative of the release of potential instability, and this is really important because it can essentially create CAPE in situ as your stronger synoptic scale forcing arrives. Now that was kind of the instability part, looking at shear distributions, in this case 0 to 1 kilometer shear. You also see this discrimination between severe and non-severe events. Overall, severe events tended to have stronger 0 to 1 kilometer shear, and this is consistent with some of the prior environmental-based work. But the difference here is that the shear is relatively constant over time, particularly when that's compared to CAPE. So overall, both of these show discrimination. It's just the trends over time change a little bit between the events and the non-sphere events. So following on from the process studies, the NWP studies here are focused on the differences in solutions across varying convection-allowing resolutions. And this is just the example of one case here. So on the left, we have the observed radar, while we have 3 different model domains on the right, starting at 3.6 kilometer, dropping to 1.2 kilometers, and then finally to 400-meter grid spacing. And regardless of grid spacing in these 3 cases, it does appear that all domains handled the convective characteristics in the mode pretty well, aside from minor timing and location differences. Although obviously as you go from 3.6 down to 400 meters, you're going to get the detail improving quite a bit. But overall, they all do quite a good job. The differences come a little bit more clear when you start evaluating fields such as 10-meter wind speeds. And based on the distributions of 10-meter wind speeds as an example, it becomes clear that there is a fairly large difference between this 3.6 kilometer and 1.2 kilometer grid spacing. But when you drop from 1.2 kilometers to 400-meter grid spacing, you don't really have much of a difference at all. It's essentially indistinguishable at that point. And there was one other case, there has been so far one other case analyzed, and it shows pretty similar differences here. And these results overall suggest that there is a convergence of the solution somewhere between 3.6 kilometers and 1.2 kilometer grid spacing, at least for sensible hazards. So it may be that dropping to 1.2 kilometer grid spacing helps you out a bit in terms of determining the potential for severe hazards. But ultimately, jumping down to 400 meters, it's not really cost effective in terms of computer resources because it doesn't offer you a lot more in terms of the actual solution and in terms of guidance. So additional analysis is being done on a handful of other cases. I believe there are about 7 to 9 cases that were simulated, and only 2 have been looked at so far. But this will hopefully help potentially corroborate these other findings as we start to analyze the other cases. So now getting into the second set of process studies, the idealized simulations. First, I want to recall some of the motivation from before. So first of all, discriminating between tornadic and non-tornadic high Sheila Cape convection, it's a considerable forecasting challenge. Ultimately, there's not much skill, especially as you get farther away from radar, discriminating between these 2 cases, because convection tends to be shallower, it tends to be smaller, and it's not resolved very well by radar. And while we have identified some discriminatory environmental features that could help with the near-term forecasting, we don't really have a rigorous dynamical basis for them just yet. So, therefore, the goals of this study were to first determine where in this CAPE or lapse rate and shear parameter space you're most likely to get strong, long-lived, low-level vortices to form, and second, to determine what, if any, precursors there are for the development of these vortices and their sensitivity to different environmental features. And it's really important to understand the links in the chain between the initial development of convection to the production of the stronger near-surface vortices that could potentially produce tornadoes or damaging winds, because only then we can start to determine what's missing in some of the cases. And the control base state environment for these simulations is shown on the right there. Just under 500 joules per kilogram of surface base and mu cape. Got 30 knots of 0 to 1 kilometer shear and a considerable amount of deep layer shear. This sounding is based on the high Sheila Cape composites we worked on, some Vortex Southeast soundings that have been launched over the last couple of years, and also soundings that we've released from NC State University in advance of high Sheila Cape convection. We actually have kind of a side field project ongoing here. We had about 50 balloons we got through an NSF grant, and we've been slowly launching them over the course of a couple of years ahead of high Sheila Cape convection. Haven't been a lot of good cases, unfortunately, but we have found some interesting features, and largely they are shown, at least the initial environment is shown here in the control base state. Now, the sensitivity tests that we subsequently did were guided by the results of these prior environmental studies, which did lead to the development of the Sherburn and the Mosh. And in particular, we focused on varying the low-level CAPE, which in this case, because nothing else really is changing, that's equivalent to varying the low-level lapse rates. And also the low and mid-level shear vector magnitudes are varied. So this leads to a matrix of 7 different simulations that overall encompasses pretty much the parameter space that we've come to expect from these cases. You can see the slightly different shapes of the photographs. The changes in lapse rates are fairly subtle. Doesn't change a whole lot, it seems, but it changes the 0 to 3 kilometer CAPE from 40 joules per kilogram to 6 joules per kilogram. And although the magnitude here is changing for 0 to 1 and 0 to 3 kilometer shear vector magnitudes, the orientation of 0 to 1 and 0 to 3 stay the same. But the photograph shape does change a little bit, as you can see here, whether you decrease low-level shear or increase mid-level shear. Those photographs are shaped about the same, as are these other two here. And that could potentially be leading to some of the interesting findings that we've had so far, which I'll touch on here shortly. So based on some preliminary analysis, we have developed some informed hypotheses. First, it appears that you need a strong low-level updraft of at least 20 meters per second in the lowest 2 kilometers or so to get the development of a strong low-level vortex. But it doesn't seem to be the only factor, because there are plenty of cases where we have a strong low-level updraft, but we don't have a vortex that strengthens to roughly 0.05 per second of near-surface vertical vorticity. Also, it was determined that as you increase the low-level shear vector magnitude, at least to a certain threshold, you get an increase in the number of strong low-level updrafts and also the number of near-surface incipient vortices. So the combination of these two factors ultimately increases the chance that one of those vortices will become strong, basically have an incipient vortex that finds itself under a strong low-level updraft and is stretched to what you call mesovortex strength in this case. Now, if you increase low-level CAPE or steepen the low-level lapse rates, you also get an increase in the number of strong low-level updrafts, but it also increases the strength of those updrafts. So again, you get an increased probability overall that one of these incipient vortices will strengthen significantly to mesovortex strength or potentially even tornadic strength, although that's not resolvable in these particular cases. Now, just to provide some qualitative comparisons between the cases, here's a snapshot of cold pool strength and reflectivity of the 6 non-control simulations. And I want to note that 4 of these actually have fairly similar mode if you just eyeball it. So the increased low-level shear, decreased mid-level shear, and both of the CAPE tests. The decreased low-level shear and increased mid-level shear here, simulations look a little bit different, a little bit messier. This is overall expected for the decreased low-level shear. You would expect overall lower or weaker organization. But the increased mid-level shear simulation is quite a bit weaker than what we initially expected. We suspect this might be related to the orientation of the 0 to 1 kilometer shear vector compared to the 1 to 3 kilometer shear vector, which could ultimately impact the linear dynamic vertical perturbation pressure gradient acceleration terms, which are key here in terms of the updraft strength. But overall, this is still an open area of research. But as I mentioned, the other 4 simulations all show pretty similar evolution, which is a general QLCS mode with some embedded supracellular features throughout. And looking at the rotation tracks, both of updraft helicity in the shaded here, the shaded grayscale, and the near surface vertical vorticity, which is in the colored contours, the embedded supracellular features again become apparent, as do the relative production rates of these near surface incipient vortices that I mentioned, these initial weak vortices that can find themselves under an updraft and strengthen. So as noted, the increase in low-level shear vector magnitude or low-level CAPE do indeed increase the strength and number of the rotating updrafts and also the near surface vortices compared to their relative counterparts here. Interestingly, the decreased mid-level shear vector simulation is actually the strongest, which we think may be a result of the convection's close proximity to the initial cold pool, which was used as the initialization mechanism in these particular simulations. But this, again, is still an open question. It's a work in progress, but it's certainly interesting that the decreased mid-level shear would be the strongest. So it's just another sensitivity, that cold pool strength and proximity to that, that we're not controlling for here, but potentially makes a pretty big difference overall. And we've also started looking quantitatively at updraft characteristics using an updraft tracking algorithm. And basically with this, you can largely confirm the findings that we just looked at. So in particular, the number of updrafts does indeed increase if you look in the red versus the pink as you increase the low-level shear vector magnitude. Same sort of thing as you increase low-level CAPE or steepen those lapse rates. And the darker blue compared to the cyan here. And additionally, the updrafts tend to be a little bit longer lived, shown on the x-axis, and a little bit stronger when increasing either the low-level shear or a level CAPE. And lastly, I'll discuss the statistical modeling work that's still in progress. A couple of the questions here really boil down to, are there any statistically significant differences in the environments that produce tornadoes and those that don't when you're looking at operational grid lengths? And if there are, what statistical techniques are best at determining these discriminatory variables? So there are several techniques that are being used, as shown here. We use clustering techniques, linear regression, and also some statistical models similar to the MOS. And overall, you know, I'll show some results here shortly, but the results are generally pretty similar to some of the findings we've had from kind of the environmental studies and also the process-based studies. And this is an example of one of the techniques here on the right. So this is a dendrogram. This plot is called a dendrogram. It basically shows the correlation between each variable here on the x-axis and every other variable that was tested, and then groups these variables or clusters them based on how similar they are. So the idea here is that you want to remove any strongly correlated variables before you start this statistical test to ensure that they're not really counted twice, so to speak. And there are indeed a handful of variables that show up as discriminatory when you use various techniques or various data sets. And a few of these are shown here. These all seem pretty reasonable, and as I mentioned, they're consistent with our prior findings. For example, the 300 millibar divergence here tended to be stronger in the tornado cases than in the non-severe events. So this could be a proxy for upper level forcing or just forcing for ascent in general. The cloud-based pressure here, or basically the LCL, tended to actually be lower for nulls, which initially may seem unintuitive, but it's consistent with the near-surface cooling that we observed in the simulated non-severe events, and is also likely combined with increased LFC, which would make it more difficult, basically, to produce the tornadoes. And additionally, if you look at the LCL distribution for the tornado cases, it's still very low in almost every case, somewhere between about 1,000 and 960 millibars, roughly. So in all these cases, you're going to have low LCL, so that's not really a discriminating factor. It's not a drawback for the tornado cases. And finally, the typically lower sea level pressure in tornado events, that could just be a proxy for synoptic scale forcing, could be a proxy for shear, increased shear, or it could be a proxy for enhanced high theta E advection. So overall, there's not anything too surprising that's come out of the statistical analysis just yet, but it'll be interesting to see what other variables start to fall out as we continue this analysis here. So I'm going to give a summary. I think I'm right about 30 minutes now. Just as a reminder, there are 5 different components to this. So we had the composite maps and parameters, first of all, and results from this can be found in Sherburn et al. 2016 in Weather and Forecasting. ultimately, we found that favorable environment in terms of lapse rates and shear, along with the strong synoptic scale forcing for ascent, was critical in determining whether you're going to have a severe or non-severe event. And we've distilled these factors into the MOSHI parameter that is available in beta form on the SBC mesoanalysis, though as it is in beta form, we may make some adjustments in the near future to tune it a little bit better for use real time. The first process studies, those are provided in the King et al. 2017, also in WAF paper. The key findings here were you had that zone of rapid destabilization, which was small temporally and also spatially ahead of the severe convection. That could potentially be due to either or both the low-level theta E advection or the release of potential instability. And that may differ from case to case as well. The NWP studies, which are still kind of a work in progress as well, found that 3 different grid spacings from 3.6 kilometers down to 400 meters all represented the convective mode and structure of high shear low cape convection pretty well. But somewhere between 3.6 and 1.2 kilometer grid spacing, you had a convergence of the solution where you couldn't gain a whole lot more as you continued to drop that grid spacing. The second process studies, which are the idealized simulations, the focus here was the sensitivity studies aimed at understanding these previous discriminators that we found in the composite map study and also to an extent the first process studies. And we found that increasing either the low-level shear vector magnitude or steepening the low-level lapse rates appears to increase the potential for strong low-level updrafts and vortices to interact, and thus the potential for producing a stronger near-surface vortex. And finally, with the statistical studies, this is still something that's very much in progress, but there are several factors kind of corroborating these prior findings. Indicate the large-scale forcing and low-level stability, again, are among the most important considerations, so it goes back to the MOSH parameter and the findings from the composite maps and also the process studies. So overall, there's a lot of consistency in the signal here, and I think we're improving our confidence in what discriminates between the severe and non-severe events pretty well. So some of this has already been transitioned into operations or is in the process of being transitioned to operations, and we're looking forward to seeing how the remainder of our findings can be transitioned at some point in the future. So I'll open it up to questions now, and if you have any additional questions that we can't get to here today, I have my 2 email addresses here. I'd be happy to take any questions after the fact. So thanks again to the VLab Forum for having me, and please ask any questions that you have. Thanks. Okay, thanks, Keith. I really appreciate it. Great summary, good talk, lots of stuff to chew on there. While John's looking for people raising their hands in the GoToWebinar, I'm going to take host prerogative to ask the first question. So boundaries, you know, shown often increasingly, I think back to many vortex experiments, and I'm not sure about vortex southeast, but I want to ask you about that. You know, critical potentially critical in discriminating tornadic versus non-tornadic storms, but I didn't see, you know, anything that jumped out in your analysis that addressed, you know, the existence of low-level boundaries in discriminating. So, did you look at that, or is it out of scope? Or I think in terms of the composite maps, you know, they're probably a little bit coarse to really resolve a lot of those features. You could definitely see where you had a stronger surface trough, you had a stronger temperature gradient along some of these cases for the events versus the non-events. In terms of the mesoscale boundaries that are around, or something like a wedge boundary, which is big in our area here in Raleigh, you know, those would probably be a little bit too fine scale to really be resolved or to come out in the composite maps. They'd probably be smoothed a little bit. I think based on the idealized simulations that we're doing in the second set of process studies, the proximity to the boundary is going to be very important. You know, I wouldn't have expected that decreased mid-level shear vector magnitude case to have the longest lived embedded supercell. I wouldn't expect it to have the strongest near-surface vortices. I think a lot of that is tied to just its proximity to that boundary, and it's a stronger boundary because it was the initial one. It wasn't the system-generated cold pool after the fact, which was a little bit weaker. So I think that zone of baroclinity there right along whatever boundary it happens to be, whether it is a wedge front or the cold front, that's really a focus for the development of these incipient vortices that could then be strengthened by the strong low-level updrafts. And so far in the process studies, I think we've found that it's not necessarily just one method where you can get a strong low-level vortex. You can get them through kind of your typical supercell type of formation mechanism where they develop very close to the downdraft and the updraft interface and can then be subsequently strengthened. With these QLCSs, we found that you just kind of have them all the time. They're just always there, these weak vortices, especially when you have higher shear. And just basically the interaction between the updrafts and those vortices is what causes them to strengthen. So I think it is a very important consideration and something that we're unfortunately not really accounting for or testing the sensitivity of in our process studies, but I certainly think it's worthy of future work, trying to nail down what exactly the role of those boundaries are.
Okay, thank you very much. So let's go. I think we got Matthew Bunkers going to be unmuting you. Got your hand raised. Now we'll go to Steve Koch. Matt, are you there?
Yep, I'm here. Yeah, nice job on the presentation, Keith. I had a question about your time series. In particular, how did you pick your points for the 3-hour changes with respect to time? When was time equal 0 during the evolution of the severe convection? And then where was your point at time equal 0 for the severe convection?
Thanks, Matt. That's a good question. So this was work that was kind of piloted by Jessica King, who is now graduated off in the real world. But what she did was, based on the different case, she took a grid of 7 by 7 points. And each of those points within the box, she calculated the CAPE change relative to when the convection arrived there. So it's somewhat dynamic based on the different case, the system motion, and basically where within that box it was. So ultimately, you had bigger differences as you went farther north in that box because you had the better opportunity for more destabilization, where it was initially a little bit weaker CAPE and more stable. Farther south, you may have had less change in CAPE overall, but there was higher CAPE to begin with. So the time series are basically an average of those 49 points for each case, which did vary based on the character of convection and also basically how quickly it was moving.
Okay, thanks. Thanks, Keith, and thanks, Matthew, for the question. Steve Koch, can we unmute Steve? Go ahead, Steve.
Oh, am I unmuted now?
You are. Go ahead.
Okay. That's a really intriguing talk, and keep that very relevant to the mission objectives from Vortex Southeast as well. One of the more intriguing things you discussed with us today was the trend analysis, particularly the one I focused on was the updraft, the vertical velocity trend showing significant increases in just the hour or so before convection developed. And I'm wondering if you looked at the nature of that updraft forcing. Was it associated with some identifiable mesoscale process that may be related to the front, like such as frontogenesis, or associated with some other process? I don't expect it was related to a boundary other than a frontal boundary, because you just addressed that question, but could you say something about the nature of the updraft forcing and why in the severe cases you see such a rapid increase in that compared to the non-severe?
Yeah, that's a very good question, Steve. Thanks for that. I believe that's still somewhat of a work in progress. That was something that Jessica King was looking at before she left. It's not something that ended up getting into her thesis or the journal article. But based on the composite maps that we're working on, which may kind of be representative of the process studies, overall we had very strong upper level divergence, very strong low level convergence, and also just generally frontogenesis basically co-located with where the strengthening convection occurred and where the destabilization occurred, especially in the low levels, the 0 to 3 kilometer cape. So overall, we don't have, I guess, a definitive answer on that just yet, but I think it's probably a combination of some synoptic and also mesoscale features. I mean, we also had fairly good warm air advection occurring throughout the warm sector, as well as noted by the low-level theta E advection, so that could have played a role. Basically, it's tough to discern right now what the key factor was. I will note, though, kind of following on from this CSTAR project, there's going to be another CSTAR project starting in the fall. I think it's, again, another 2-year period, but it's basically going to be addressing a lot of the questions that we've yet to get to here and yet to answer in this project. And again, it's going to be focused primarily on the low-top severe convection across the Southeast. So it kind of goes hand in hand with the Vortex Southeast stuff, which I know another student here at NC State's working on right now. But hopefully we can address the questions like that and things like boundary interactions in that subsequent project.
And just, I'm sorry, real quick follow-on question. The rapid increase of vertical velocity was not attributable, I presume, to convection itself. It was pre-convective?
I believe so. Yeah, I think it was. I'd have to go back and ask Jessica about that. But I'm thinking it was at the 9-kilometer grid where she calculated that, which would still have a little bit of convective contamination, but I think most of it was prior to the convection's arrival.
Okay. Thanks, Steve, for the question. Do we have another, John, do we have another?
We do not.
Do we have any chat questions?
No.
All right, I'm going to follow up with another one. So I find it's helpful to look at the extremes and these types of studies. So did you look at how your results compared to low shear, high cape in that parameter space? And I'm curious, you showed your bullseye for the high shear low cape being in the Southeast. Where is the bullseye for low shear high cape, or if you know?
That's a good question. I do not know, actually. It was something we started looking at a long time ago, and we never really got much traction on it.
Well, it could be in the Southeast as well. I mean, it might be a seasonal thing, right? I mean, if you're high shear, it looks like you're in the winter, which makes sense. You're going to have the biggest synoptic forcing in the winter down there. But maybe in July or August or something like that, when the upper level diminishes, certainly going to have lower shear and probably juicy cape coming up from the Gulf. It would be curious to see that kind of a comparison and might be enhancing your publication results if you could show that. I mean, I would suspect they're different dimensions to those two extremes.
Yeah, I'm sure you're right. And you make a good point about the Southeast during the warm season. Certainly in terms of damaging winds and potentially hail, yeah, probably the high cape, lower shear, I guess bullseye would probably be in the Southeast. I mean, we get a ton of microburst type events in the Southeast where you have a lot of cape and practically no flow. So I would probably agree with you there in terms of the winds and potentially the hail. I'd say for tornadoes, I'm not as sure because we don't get a lot of tornadoes with those types of environments here in the Southeast. Potentially farther north into the Ohio Valley, you could have a little bit more of that in the summertime. That's a good question, and I will take that to heart for sure. I will note that we looked a little bit at the high cape, high shear part of the parameter space, and generally speaking, I mean, it's kind of what you would expect in that there's more instability and less forcing or weaker forcing in that high cape, high shear part of the parameter space when compared to the high shear, low cape. It's not something we included in the manuscript, but it's probably something that I'll touch on a little bit in my dissertation and potentially in future work as well.
So that would be like a Birmingham 1998 kind of a situation, basic classic supercell Oklahoma variety sort of environments, right?
Right, exactly.
Okay. Do we have any questions in the room? Go ahead, John.
So Keith, you mentioned that a number of these findings were finding their way into operations being transitioned. Can you give us an idea of how that transition takes place? What form do these findings make their way into operations?
So it depends whether it's at the national scale or the local scale. I know initially when we came out, we developed the Sherb parameter back in 2013 or so now. That kind of started locally. There were several local WFOs that were interested in incorporating the Sherb into AWIPS, so we could start to basically get real-time forecasts of the Sherb. It was also something that we started to plot on some local pages at NC State University. Matt Parker, who is one of the PIs for this project, he was plotting them on his website. So that was kind of where it started. We provided some examples through conference calls. People started to get interested, and we found ways incorporated into AWIPS or other means. We also did a handful of case studies during that last CSAR project, which ended in 2013. And throughout that, we got a sense of how well it performed in those case studies as well. So overall, it provided some confidence going forward. At the national level with SPC, you know, they kind of took on plotting the Sherby and the Moshi in the SPC mesanalysis on their own. It was something that they wanted the different WFOs to be able to investigate real time and to test and to assess basically how useful it was for them. There's been mixed results overall. Like the Sherby, as I mentioned, it had a fairly large false alarm area, and there were, I think, some concerns that certain operational forecasters may have been using it too liberally in the absence of some other considerations. So overall, I think that having these parameters on things like the mesoanalysis or in AWIPS is very helpful in terms of the development and also the future adjustments to the parameters. Because having an operational eye on things will let you see a lot that you don't see when you're doing the analysis. You know, when we first developed the Sherb parameters, that was all based on like point soundings or point values of these different terms within the SPC mesoanalysis. It wasn't based on, you know, spatial fields or how they change. So getting a look at the maps, the plan view maps real time, and assessing what the strengths and weaknesses are helps out a lot going forward and allows us to make adjustments in a more timely fashion.
Great, thank you.
Steve Koch has his hand up again, so we'll unmute him. I think he's got another question. Steve, you there?
Yeah, if you don't mind, I'm sorry, real quick question. Not to get in the way of other questions, though. My question has to do with verification. And so as the Vortex Southeast Program Manager, one of the things that I talk with Eric Rasmussen about frequently is what do we need in the field to verify these model forecasts, like your high-resolution war forecast that you showed us today. And looking at the key things that came out of your study that were discriminators between events and nulls, some of the things that popped out were low-level convergence, that strong updraft intensification, the maximum low-level CAPE, conditions for the release of potential instability, just to name some of the bigger ones, right? And my question is, what do we need? Could you recommend, what do we need observationally to verify these model forecasts that suggest that these are the discriminators? And realizing, I don't know if you know, Keith, whether we do have wind profilers and boundary layer thermodynamic profilers in, particularly in northern Alabama, as part of this project. But would you recommend something different, or, how do we go about verifying and knowing that these are really true features in the real atmosphere?
That's a great question. And, we helped out, Matt Parker, myself, and a couple of the other students helped out with Vortex Southeast last year. And we were able to coordinate some of the balloon launches on a handful of the cases. Our general focus for those balloon launches was to try to capture some of this destabilization, whether it be a result of the advection or the potential instability. Unfortunately, we didn't have a whole lot of success with that last year, and we haven't had much success with it either here at NC State. There have been some cases here at NC State where we've been able to capture things like mall structures ahead of the convection. So we know those types of things are there, and we have a sense that potential instability is being released in some of the cases. But ultimately, I think really anything would help at this point. We don't have a whole lot of observations of these cases and don't have a whole lot to go on. Based on what we've been looking at with our soundings here, the mesoanalysis sometimes is very good, sometimes it drastically underestimates the instability of the CAPE. So I think just about anything would help. I think it'd be nice to have a dense surface network of observations ahead of these cases so we can get a sense of how rapidly the surface theta E and surface theta and mixing ratio are changing, how rapidly that advection is taking place. I think having a dense network of radiosondes would be great, so we get a sense, especially west to east or north to south, where that potential instability is being released and how rapidly it's doing so and how intense it is, how much CAPE is being produced. And I think the profilers are great as well. I mean, I think overall the shear and the kinematics are a little bit more stable, as I noted before, than the instability. But yeah, having a sense of where that best convergence is going to be, since the low-level convergence was one of the key factors that we saw in the composites, that would certainly be important. I mean, I think at this point, just about anything would be useful. And I think something like Vortex Southeast is great, and I hope that we continue to do that type of work, especially on these less predictable events going forward. So I appreciate that question, and hope we can work on it in the future.
Okay, thanks, Keith. Thanks, Steve, again. John Crockett has one quick.
Hi, Keith. This is John Crockett at the MDL. I work with the auto nowcaster system, which just became operational in December. I'm struck by how much or some of what you're doing is similar to the kind of weighting and summing that ANC does. I'd like to know if, in particular, if your choice for some of your parameters, like say the advection, CAPE, and another, were based solely on your own considerations, or, for example, some of the work that was done to create the National Convective Weather Forecast, and which has parallels in ANC. The parallels are striking. How did you come up with your ideas for this to begin with?
Well, good question, John. Thank you for that. And I don't know a whole lot about the auto nowcaster, so I'll have to take a look at that more after this call. But
I'll be happy to send you any documentation.
All right, thank you. I appreciate that. I'll be in touch. Yeah, in terms of the composite maps and the different parameter-based studies we did with that, that was largely eyes open to anything. So we took basically all the fields that the NAR had available and then several other fields that we calculated in post-processing, and basically found what fell out. Looked through a lot of maps, just kind of eyeballing the differences, but also we did some skill score tests for the different parameters just to see what fell out as the most skillful, and it happened to be mostly things that we had looked at before. There were some new things, but again, it was largely eyes wide open. In terms of the process studies, particularly for the wharf simulations, that I think was more so based on what the wharf had available and whatever Jessica King found as the most interesting. And I can't speak a whole lot to what why she focused on the things that she did, but these were sort of the things that popped out as immediately important or potentially relevant, and so that's kind of what we rolled with, I think. But yeah, I'm certainly interested in learning more about the AutoNowcaster and potential other ways to go about this. And just to follow up again with the statistical studies, that was the same sort of thing. They used the same data set there that we use in the composite maps. So that again is largely eyes wide open, just seeing what falls out.
Okay, I would be more than happy to share information with you in this regard. I do have one follow-up, and are you specifically looking for a way to, is the work you're doing, the end result meant as a means to forecast severe weather, specifically severe weather?
That's generally the goal. Yeah, I mean, that was kind of the goal going in, was to be able to discriminate between those cases that would be severe and those that wouldn't, which would produce, your sensible hazards, and those that wouldn't. And that goes from, a couple days in advance to, including the model forecast and things like that, down to the storm scale near-term warning operations. So that was the general goal that we had in mind when we started this project.
Okay, thank you.
All right, we're going to have to cut it off there. Again, I want to thank Keith for an excellent talk, very thought-provoking and great stuff, again, coming out of the C-STAR program. Appreciate the effort down there from the folks in NC State and the local WFOs, I guess, down in the same area. Reminder, this will be uploaded shortly to the VLab Forum website, so you can share the recording with your friends and colleagues. Coming up in July, we've got July 19th, we got the Forecast Builder Project. Chuck Grief will be presenting that. In August, precipitation rate estimation based on specific attenuation. Stephen Cox is the presenter there. And in September, the FEE Hazard Service, Probabilistic Hazard Information Hazard Service Project, Tracy Hansen and Greg Stump will be presenting the results of recent testing in the hazardous weather test bed. That should be one you definitely want to attend. So we're signing off, and happy solstice, everyone.